All right, well, good afternoon and welcome to the Spring Water Seminar Series hosted by the Nebraska Water Center and some other people as well. My name is Derek Heron. It's my pleasure to introduce to you our speaker today, who is Tim Shaver. Tim Shaver is a nutrient management specialist for the University of Nebraska-Lincoln at the West Central Research and Extension Center located in North Platte, Nebraska. The emphasis of his research is maximizing crop water and nutrient use efficiency, as well as overall agronomic production. This research is conducted within a variety of crop rotations in dryland, limited, and fully irrigated systems under conventional and no-till management. Tim is originally from Colorado and is a graduate of Colorado State University. I've had the privilege of working with Tim on some other irrigation research, and I'm looking forward to learning more about his presentation today. He is going to tell us about some of his work on using variable rate information technology to improve our water use efficiency. So welcome, Tim.
Everybody hear me okay? Well, good afternoon, everybody. I certainly appreciate the invitation to come speak to you guys today about some of the things I've learned using variable rate irrigation. A quick disclaimer, there are probably several people in the room here on the engineering side of things that probably understand kind of the nuts and bolts of how the variable rate irrigation systems work and kind of the theory behind it. I'm, as Derek mentioned, a soil fertility specialist, so my interest came to be with variable rate irrigation in looking at primarily how irrigation and soil water is related to nitrogen and how we apply nitrogen. So especially in the western part of the state where we're very semi-arid and several areas are now under allocation for irrigation, variable rate irrigation became something that we became very interested in just learning how it works, trying to figure out new ways to apply this technology, and seeing how this interacts with specifically nitrogen and other nutrients that we might apply. So that's kind of how I came to be on this. And because of that, I've gained a lot of practical experience dealing with variable rate irrigation, and I've learned a lot more about how it actually works than I ever set out to. I wanted kind of a turnkey system where we put variable rate irrigation on the pivot, and I dialed up some variable rate irrigation maps and just kind of see how things happened with the nitrogen side of things. But it's kind of an emerging technology, so we've had some issues and we've learned a lot, and I've had to kind of get my hands dirty, if you will, kind of dealing with the variable rate irrigation. So I'll talk a little bit about some of the things we've learned and some of the ways we've used the irrigation as well. So just some quick acknowledgments. A lot of what I'll be talking about today is in conjunction with a large statewide study where we're really trying to figure out ways to recommend usage of variable rate irrigation in conjunction with variable rate nitrogen applications. So we have a really large team of researchers that are working on this project. Richard Ferguson here on campus, Swat Ermach, Simon Van Donk in the West Central. We've got a couple really good graduate students that have been helping us out, Darren Rudnick and Nick Ward. The USDA ARS here in town has contributed a lot to this study as well. Marty Schmer, Brian Weinhold, Virginia Ginn, Dennis Francis, and Aaron B. Ryder. They've all been a really integral part of a lot of the work we've been doing. And kind of a lot of the impetus for this study was John Deere. They have soil moisture sensors, real-time soil moisture monitoring, and they wanted to see how those sensors functioned under variable rate irrigation and to see if their sensors had a role in recommending how we use variable rate irrigation. So they've been kind enough to provide us with funding to do a lot of the research and some of the things that I'll be talking about here today as well. Okay, so this map's probably not new to a lot of you. This shows the annual precipitation as we move from west to east in Nebraska. And as you can see up in the panhandle there, up in the northwest part of the state, we're very dry, anywhere from about 12 inches or so of precipitation to about 15 or so inches of precipitation. And as we move east across the state, obviously the precipitation starts to increase to where we get above 31 inches of precipitation as we get into the southeast portion of the state. Now, where North Platte is right about here, and where a lot of the work we're doing with variable rate irrigation is located in Brule, Nebraska, which is right about here, so in the drier portion of the state, where we're at about an average annual precipitation of 19 to 20 inches or so. So obviously, as in the semi-arid portion of the state where we're drier, irrigation is very important to maximize yields, especially in corn. And as we move into the southwest portion of the state, we're starting to get into more cases where farmers are under allocation of how much or how much irrigation water they can use. So being able to variably apply that irrigation water with these VRI systems is really of interest to them. And we get a lot of questions about the systems from these farmers that are particularly under allocation. Where we're at the Rural Research Farm, we're not under any allocations yet, but I could foresee a time when a lot of the semi-arid portion of the state becomes under allocations, and where a VRI system would really help us in terms of where we're putting our water and how much water we're putting down. So here's a map that shows the irrigated cropland, approximately 3.46 million hectares right now. This also shows the primary crops grown. And you can see that there's a lot of yellow on that map under the irrigation. Also a lot of soybeans. So a lot of corn, a lot of soybeans that are irrigated in this state, obviously. And being able to increase our water use efficiency becomes of primary importance when you realize just how much irrigated cropland we have in the state. If we can increase our water use efficiency, we're going to save a lot of water. And variable rate irrigation has kind of the promise to help us do that. Here's a map of the Ogallala Aquifer saturated thickness. I'm sure a lot of you guys have seen this as well. So as we look up here at the top part of the map, this is where we have Nebraska. So again, where we are in the semi-arid portion of the state out west, we're still in pretty good shape relatively when you look at the saturated thickness. We still have quite a bit of water in terms of the Ogallala Aquifer. And as we move south and we go down into Texas, obviously that saturated thickness starts to decrease quite a bit. So even though we're in really good shape here in the state, that doesn't mean that we want to just keep pumping water. We want to be able to only apply as much water as we need to maximize our yields. And again, that's where the variable rate irrigation system comes into play and can help us use water more effectively. At least we hope it can. So here are the water level changes. This is from a few years ago. As you can see up here in Nebraska, again, we have relatively low amounts of water change in the thickness of the aquifer. So again, we're still doing pretty well in terms of how much water we have to allocate to irrigation. But as we move south and we get into Texas, you can see that there's been a pretty significant reduction in that saturated thickness. And this is what we're looking to avoid, right? We don't want this situation to occur up here in Nebraska. We want to be able to maintain levels as much as possible. And by only applying as much water as we need when we need it, that will really help us to accomplish that goal. Okay, so moving into variable rate irrigation. So there are several of the manufacturers, if not all of them right now, are offering variable rate irrigation as an option or as an integrated part of their systems. We put variable rate irrigation on the first of our pivots out at the Brule Water Lab when I first arrived about 4.5 years ago. And it was an add-on system that we were able to actually bolt on to the current pivot. And this system is still available, but they're all going to work a little bit differently. This system that we applied to our pivot is the one that I'm most familiar with, so it's the one kind of I'll be going over how it works and how we use it. But there are variations in the other pivot manufacturers, how they work. But they all kind of have the same general principle. So what we're looking at here, this is the software that's included with the variable rate system. So after we mounted all the hardware, which I'll get to in a minute here, this is the interface that you get to be able to determine how you're going to variably apply our nitrogen. Now, this underlying field here is just a Google Earth image of one of our pivots at the Brule Water Lab. And you just simply import that image into the software that they have so that you can overlay a real image of the field that you're using, just a bare soil image of the field that you're going to be applying this to underneath the grid system that you then create. So this grid system, each of these lines in the grid represents one of the pivot spans. Our particular system that we set up can vary water based on each individual span. Now that's just because that's what we spec'd it out to do. We thought that over one span for using our research purposes would be adequate. Now you can set them up to vary water based on each individual sprinkler drop if you want to, and if you want to spend the money to do that. We opted not to do that at this time. We're just on one particular span. And then you can set up the degrees to which each of these are controlled. The default is at 4 degrees, and that's what this graph here shows. So every 4 degrees, we can vary the amount of water we apply across each of the pivot spans. Now, if you look over to the left here, these are all the different rates that we can then apply using this particular software. On the bottom, all the way from a 0%, which means it doesn't apply any water, up to 100%, where it applies the full rate, and it varies in 10% increments. So for this particular system, we can back the water off in 10% increments. So we can go down to 90, 80, 70, etc. as we go across the field. Now, this system, when we first set it up, did not have a variable frequency drive on the pivot. Since then, we have added that, and that changes the rates that we can do quite a bit, because now we can, not only can we have the different percentages of water that we're applying, we can now speed up or slow down the pivot. So we really increase the level of resolution, if you will, that we can get to and how much water we can apply. But it's really simple to use, and you set up this map. As I've said, you import this picture, you download the GPS coordinates, because everything is based off of a GPS that's mounted onto the pivot, and then you can just simply click on what rate you want to apply, and then go over to each of these cells, click on these cells, and it will automatically upload that particular rate. So here's what it might look like if you were starting to make a variable rate map. So I've just got several different rates. I just looked at the different soil types. Down here we've got a kind of a really coarse soil area of the field, and I just went in and I put in a 20% just as an example. And all you have to do is just move around and click on all of these. After you have the map set up that you want, you just convert it to a shapefile, import it or move it over to a USB drive, and then you can just manually upload it to the main computer system on the variable rate system. The one we're using will hold 5 different maps, so you can just go and you can select one of any 5 maps that you might have loaded on there. However, it's really simple to delete one map and upload another one. It's a matter of a couple minutes to be able to do it. Unfortunately, with the system we're using now, it's not something that you can do over the air or wireless. I envision that it will be going to that so that you can make maps on the fly, if you will. But out at our rural water farm, we have a full-time technician who works at the farm who's schooled in how to do all this, and we can just email him a map if we want to, and he can go out to the particular pivot and upload it to the computer within a couple minutes and have that system running, invariably applying water as we move across the field. So really easy to learn. It took me all of about 10 minutes the very first time I ever used it to have my first map done, and then it took me another 10 minutes to figure out how to load it the first time. And then, of course, over the winter, I always forget how to do it. But then in the summer, again, in that first time, it only takes me a couple minutes to figure out how to reload it. But it's a really easy system to use, and there's quite a bit of modification you can do. Now, as I mentioned, these are on 4-degree arcs, but it can be modified anywhere from 1 degree to 10 degree. So with our current system out there, we could have as many as 3,600 different plots out there if we wanted to across this field. So a large amount of capabilities to look at variable amounts of water that we might apply. So here's kind of the schematic of how the system looks. So over here we would have the VRI controller, and I've got a more close-up picture of that here in a second. And then it just communicates with slave nodule boxes, and each of these boxes can do up to 8 individual zones. So if you think about it, each of these zones would be a span in our case. And then there's a solenoid that runs off of each of those that goes to a water valve, which then modulates water on and off, and that's how it varies the amount of water. So it'll modulate on and off. So if you wanted to do 90% of water, it would modulate to where it's turning off, if you think about it, every 1 second out of every 10, it would basically turn off the water. And that's how it actually varies the amount of water that's applied. Now, I mentioned that you can do this however you want to set it up. You just have to keep adding on these node boxes, because each of these can do 8 individual zones. So if you wanted to do each individual drop, you would need one of these boxes for every 8 drops. And that's where the expense can really come in. Each of these nodes is about $3,500. So to set up our pivot to be able to do 10 spans, which our pivot can do, the initial cost was about $12,000. So not really expensive at all if you wanted to upgrade a pivot to do this. That's on a span basis. Now, if you wanted to go to each individual drop, obviously the price is going to start to elevate pretty quickly. But I don't really see a reason why the farmers would want to go to that level of resolution. And most of the farmers I've talked to would really like to get it either onto a span or to a half span basis. So that still makes it a relatively inexpensive system to upgrade onto the pivot. It does take a little bit to have it installed. You do have to run lines across the entire pivot, both electrical and either water or air lines. and I'll talk about why that is here in a second. So there is a little bit of work being able to install this. We contracted a pivot manufacturer to install it, and they were able to do it for $4,000. So for about $15,000, $16,000, we were able to have everything installed and ready to go. So that was with a university discount. So when the farmers wanted to do it, it'd probably be closer to 20, but still not most farmers might even want to do it themselves, and they'd probably be able to save quite a bit of money right there. So really not really cost prohibitive if you want to add this kind of system to your current pivot. So here's an up close look at the main node box. So this would be the main box, and this would be mounted usually near the center of the pivot. And you can't see it, but underneath here is just a USB port right about, actually I think it's right about here. And you just load any USB stick on there, and just you scroll through on the menu, click OK once, and it uploads the map. And like I said, it'll store 5 of them. So really slick system, really easy to use. Should mention this is called the main box. Then there's slave node boxes. They look the same. They just don't have this control module on it because they all communicate with this box. So you don't need to be able to actually do anything with those particular boxes. You might see something interesting down here. So where all the wires are plugged into the computer, you notice that there's no color coordination whatsoever. This became an issue when we fried one of our boxes. We think that one of our boxes got struck by lightning, and they sent me a new one, but some of these wires had to be moved to different ports. So the communication was move the 7th black wire on the first box to the 13th position on the second box, and it became quite complicated really quickly. They have told me that since then they've changed that to where they have now color-coded all the wires because they've realized over time that there are going to be issues that you need to be able to get in here and work on this from time to time. And like I said, this one that we got was one of the first ones that came out, and I think together we've learned quite a bit. So here's just a picture of where that box is mounted. It's mounted in a watertight box. This is just an old piece of pipe that we mounted it to, so it's about at eye level. You can walk up and you can get in there and just deal with any of the maps that you need to load or anything that you need to change. You can see kind of on the bottom here, there is a water filter right here. This is the only annual maintenance thing we found. This does need to be drained at the end of the year. It's simple as just unscrewing it and pouring it out. If you forget to do that, which we did the first year, it will freeze and crack it and break it, and then you have kind of a mess when you first fire it up the next year. So again, kind of a learning curve that we had with it. So here's a picture of the back of the box, and here are the solenoids. So each of these solenoids will run one zone, and as you can see, there's 8 of them on this particular box right here. So on down the pivot, about mounted halfway, we have the slave box mounted, and it has, for our particular system, it only has 2 more of these solenoids to run 2 more of the zones. But each of these will run one of the zones, and you can see all the lines going into it. So for our particular setup, this is water pressure activated. So these solenoids run water pressure, and just a line off of the main line is put into here, and then it just sends water pressure to each of the water valves, which then regulate whether or not they're turned on or off to be able to vary the amount of water. There are systems that are air mounted, so they have a big air compressor that's mounted on them as well. They recommended, you can still get that, they recommended we don't do that. There's a lot more maintenance involved with running that kind of airline, because I mean you have to run an airline all the way out to the end of the pivot. So they had issues with airlines breaking over time or forming leaks or cracks. The trade-off is, and we found this out, with the water pressure valves, there's a delay in the activation. So when the GPS gets to a new zone or to a new cell that I showed you and says, oh, I need to change from 100% to 80%, there's a delay. In some cases, maybe 20 to 30 feet. So quite a bit. So if you've got one kind of area that you're really trying to maybe turn water off of, if you've got a little pond, if you will, in the field, there's kind of some setting up you need to do to make sure that everything's turning off and on where you need it to do it, because if there is that delay. Now with the air pressure system, they tell me that delay is a lot less. And now some of the other manufacturers have electrically actuated systems, and those are supposed to be instantaneous. And we are getting one of those electrically activated systems this year, so we're hoping that helps us out, especially in terms of research where we're trying to do things on very specific timings of when our water changes. So that's something that we really need things to happen rapidly. Here's what the water valve looks like. So here, these are just the drops that go down to near the ground. Here's that water line I mentioned. So this just, the water pressure here moves into the water valve, and that water valve then cycles and regulates how much water is applied based on that map that you select. Here's what it looks like mounted on top of the pivot. So each of these individual drops here have one of these water valves. Now, even if these are all in the same zone, they still have to all have this one of these water valves, because that's what regulates the water being turned on and off. And then each of those solenoids would run 8 of these, or excuse me, as many as you want, up to 8 zones. So then you can kind of see all the lines that are run up here. So these water lines, or the air lines, all need to be run all the way down the pivot, all the way to each of these solenoids. So there's quite a bit of line that needs to be run on top of the system, and then each of these valves need to be installed on top of them. The nice thing about these valves is they're only about $10 or $12 a piece, so if you do need to replace one, it's very inexpensive. The only real expense for the whole system is just the computer boxes themselves. Okay, so talking about some of the applications we're using. So right now we have 4 systems that are currently equipped with variable rate irrigation pivots at the Brule Water Lab. There are 2 farms at the Brule Water Lab. One is on the south side of I-80, one is on the north side of I-80. The one on the south side of I-80, at one point, we think there was a channel from the Platte River that ran through the field, which has created an extreme amount of soil variability. You can kind of see that on these fields, just from this picture here. You can't see the topography here. I have a topography map I'll show in a second. But this is the field that I do a lot of my nitrogen work on, and it has an extreme amount of soil variability and an extreme amount of landscape variability as well. We've got a system that we just purchased for this field here that will be going on here in the next couple weeks, so we'll be able to vary water here as well. And then this one is on the list for next summer. We're hoping to get a variable rate system put on here. This was the original field that we installed the system on, the one that I've kind of been showing pictures of. That pivot was about 30 years old, so this year we're fortunate enough to upgrade to a brand new pivot, and we've selected a pivot that has an integrated variable rate system already in it. So we'll be moving away from that particular system that I just showed you to one that has an electrically actuated system, so we think it'll be more accurate. And it'll be nice, I think, also to have one everything is built together, all made to go together as one. So we got that brand new one going on here, and they're actually building that as we speak. So we'll be learning a lot about the new system here really soon. Here's our Brule North Farm. Now this one's up on the step when you get out of the Platte River Valley. So here we have very flat, uniform soils. And we have variable rate systems on both of these pivots. And up here, this allows us, on the South Farm, we're really trying to look at quantifying soil variability and then managing both water and particularly nitrogen based on that variability. So we're trying to figure out some things in terms of recommendations on how to use variable rate systems, how to vary water most effectively, and then how to integrate that with nitrogen. So that's where we're doing most of that work. On the North Farm, with these very uniform and flat soils, we're doing a lot of work looking at different hybrids, different water efficiencies and hybrids, things where we want very uniform soils so we can compare things such as that across different water levels. So 2 different areas of the field of the farm where we can do a lot of different types of research projects based on water. And almost everything we do out at Brule, hence the name of the Brule Water Lab, has something to do with water in one way or another. We also have quite a bit of dry land. We've got all this area up here is in dry land, so we do a lot of work in dry land up on this part of the farm as well. So here's a picture of the West Central Research and Extension Center out of North Platte, and this is where I'm stationed out of. We are moving that pivot that I just showed you from the South Farm to this area right here. This used to be a solid set irrigation system, and we will now have that pivot right here. And we are refurbishing it so it'll work well, and we're also keeping that variable rate irrigation system on there. So we will have a full pivot right here where we'll have variable rate capabilities as well starting this summer. We have a linear move right here and a linear move right here. And the plan is for next summer to have variable rate systems set up on both of these as well. They don't have to just be on center pivots. They can be on linear moves as well. So the software just looks like a rectangle instead of a circle, but it all works the same way. And then right here, we have subsurface drip irrigation, and we can vary water. Basically on each of these little plots that you see, we can vary the amount of water we put there as well. So we have an extreme capability, and I would say probably the best in the nation in terms of being able to do water related to variable rate irrigation and looking at limited water capabilities. I have not talked with anyone who has anything near the capabilities that Nebraska has out at the Brule Water Lab and now out at North Platte as well. So we're very excited about that. Okay, so some of the specific research questions we've been kind of thinking about with using these variable rate irrigation systems. So if VRI is implemented, what are the interactions with nitrogen supply? So I've talked about that a little bit. As a soil fertility guy, this is my biggest interest, is what happens when we start to, if we get a good idea of how to vary water across the field based on its variability, its soil variability, based on trying to increase the water use efficiency, based on maybe allocations where we can only put so much water out in the field in certain areas, how does this affect our nitrogen management? Because we can variably apply nitrogen as well. So what's going to happen there? What kind of interactions do we need to start to think about? Can we develop recommendations for combined spatial and temporal management of water and nitrogen supply? So again, can we have a recommendation that says if we're applying X amount of water, we need to apply X amount of nitrogen, and how those are going to tie together so that we can maybe not maximize yields, but maybe maximize our efficiencies, maximize water use efficiency, maximize nitrogen use efficiency. And the other thing we're looking at is how can sensors monitoring both soil and plant water as well as nitrogen status be used most effectively? So if we're going to quantify the soil variability, if that's going to be how we decide how much water we want to put down, how can we use crop canopy sensors? How can we use soil moisture sensors? How can we use any other sensors, maybe thermal sensors, sorry, or even height sensors? How can we use these sensors to help us, to give us information on the variability we have in the plant growing so that we can then variably apply water and or variably apply nitrogen so that everything works together. Now, as if that wasn't complicated enough, we brought in the landscape position to this as well, because as I mentioned, that field on the South Farm has quite a bit of topography. So now what happens when we bring into the fact that we're going to have water moving in the field, right? From if we've got an upslope to a bottom area and our irrigation water isn't going to just stay where it's put, then how does that affect how we might start to answer some of these questions? Okay, so as I mentioned, here's the Brule Water Lab. You can see there's quite a bit of variability. This field is unique in that right down here through the middle is where we think the river channel ran. So, and down through the middle, this is the lowest portion of the field. And through here, we have very shallow soils. In some areas, we might have 6 inches of topsoil, and then we'll hit gravel. It's really fun to install neutron probe tubes when you hit gravel, I can tell you that. So our least productive soil is actually on the lowest portion of this field. As we move upslope away from that, our soils start to become far more productive and far better, deeper soils. For an example, last year in our highest nitrogen areas, highest water areas, and our best soil right around in here, we had yields approaching about 300 bushels per acre right here. On our lowest productive areas, under the same nitrogen and water conditions, we got about 65 bushel. So a fair amount of variability in this field that we're trying to manage for. Here is the soil apparent electrical conductivity, and you can kind of see it speaks to what I was just talking about. Got a lot of variability, and this is just a really good measure of the texture that we have. So a lot of textural differences as we kind of run down through this lower portion of the field. And then as we move out of there, you can see we get to our far more productive and our far better soils. So just a lot of variability that we're trying to deal with on this field. And if I'm honest, kind of too much for some of the research questions that we're trying to answer. This field has been a challenge, to say the least, to try to quantify some of its variability. It's by far the most complicated field I've ever done any work on. I like to look at the bright side of it. I think if we can answer a lot of questions and develop a lot of techniques for this field, I think we can do them for the majority of fields in Nebraska, just because of how complicated this particular field is. So one of the things we're also looking at is we can predict the plant available water with that electrical conductivity measurement. So as I mentioned, that electrical conductivity is a good correlation for the soil textures that we have. So if that gives us an idea of what kind of texture we have, we can then get an idea of what kind of water holding capacity those textures give us, and we can start to develop kind of a map based on irrigation we might need based on the relative water holding capacities of the soil. And then, as you can see all these dots on here, these are areas where we would have neutron probe tubes or watermarks or other soil measuring, moisture measuring devices that would help us kind of relate real world levels to what our estimates or our models tell us. So this is one potential way, and kind of the leading potential way right now that variable rate irrigation prescription maps are made by dealing with that potential water holding capacity of the soil. So we're looking at this as one of the potential ways that we can do it. Here's the topography of that particular field I just showed you. So again, here's that low-lying area. And then as we move up out of there, so again, just a lot of landscape positions as well. And one of the reasons we wanted to initially use this field is because with the slopes that we have, you know, what happens if we apply water at a variable rate right here, where it has potential to move down the slope? How does that affect the kinds of things that we're trying to measure and the kind of things we're trying to develop? So here's the sites where we've started to do this work. As I mentioned, this is a statewide project with a lot of different scientists. So we also wanted to bring into account the precipitation gradient that we have in Nebraska. Nebraska is really unique and great to work at if you're interested in water, just because of this gradient. You know, I'm sure you guys have heard this before, but there's a larger increase in water from the western edge of Nebraska to the eastern edge in precipitation than there is from the eastern edge all the way to the Atlantic Ocean. So just an extreme amount of precipitation variability as we move across the state, and that's what we were trying to capture with this study. So obviously I've been talking about the Brule Water Lab, where we have one of our main studies. For the first 2 years of the study, we were on a producer site who also had a variable rate system that he purchased for himself up near Scotts Bluff, where it was even a little bit drier. We have a variable rate system mounted on a linear move at the South Central Ag Lab to try to bring into account the kind of the wetter areas. And then we've also have a cooperator up in Hamilton County that we've been working with to try to answer some of these questions as well. So we're also trying to bring in the climatic factor as well as to how this might change. You know, because if we figure out something that works at Brule in terms of our of a prescription map for water, well, we only get about 19 to 20 inches of precipitation there. Is that going to function the same as if we're trying to do that, you know, in other areas of the state where we have higher amounts of precipitation? Here's kind of how our treatments look. So this was the first year. So all of these strips here are nitrogen strips. So you can see we had 75, 125, 175, and 225 pounds of N randomly assigned, and these went completely through the field. And then on top of those, we varied our water. So we looked at both 40% of evapotranspiration, 70% of evapotranspiration, and 100%. And this 100% would represent our full irrigation. And we ran those as the pivot came across each of those strips, so that we had several different iterations of each water and nitrogen application rate across the field. This was the first year of the study. As you can see, as we kind of get down in this part of it, it became kind of complicated as to where your plots were, just because of the geometry involved. And I actually had to break out a compass and a protractor when I designed this for the first time, which I hadn't done since high school, so that was kind of fun. But what we did in later years is we started to plant in circles, you know, which we're easily able to do now with the GPS equipment. We can plant in circles, and now our water strips can run the length of it's in the same direction as the corn, which has made it quite a bit easier to apply our treatments. So like I said, this was the first year of the study here. This is what it looked like. Each of these individual lines here is one of the plots we had with a different nitrogen and different N rate. The second year of the study, we moved over to here, and again, this slopes from an upper slope to a bottom slope here. And then in the third year of the study, which was this year, we started about here and moved down here, which also is upslope to bottom slope. So we've kind of been moving around the field trying to give us the best chance for a nitrogen response. We don't want to put the study on the same portion of the field year after year. I mentioned our soil moisture sensors, so we've been using 3 kinds of moisture sensors. Unfortunately, as you guys can see, this is a pretty large study in terms of the area it takes up. And unfortunately, we just didn't have the manpower to put soil moisture sensors in each individual plot, so we kind of had to just do our best with it. But in each of the plots where we did have a soil moisture sensor, we did all 3 of these. So we did neutron probe, which is kind of the standard by which everything is based on. We did watermarks, And we did, this is the John Deere CropSense sensor. So this is the one that is real time. You can see it has an antenna on it. It uploads data, I believe, every hour to the internet, so the farmer can get online and check and see what his current soil moisture status is in that particular location. So we were evaluating how well this sensor works, and that's what SWAT did a lot of work based on that and has done a lot of work with that. But the other thing we wanted to look at is if we're going to use these sensors to help us determine soil moisture content and therefore help us determine how we're going to variably apply water, how many of these sensors do we need to have in the field? Are we going to turn this field into Swiss cheese before we get any kind of indication of how much soil moisture we have? So we've come to the realization there's probably going to be a fair amount of modeling involved with this as well, trying to use sensors in the most effective way we can. And then the other issue we've ran into, at least at the rural field site, with the extreme amount of variability that we have, we'll put these sensors as close to each other as we can so that they're not disturbing each other, but we're still seeing variability in our soil types. We can get everything in about 4 feet, and we'll still have a completely different soil type from where the neutron probe tube is to where the watermark sensor is. So we're trying to compare apples to oranges in some cases based on what that soil moisture is. So while these sensors all function very well and give a very accurate reading of your soil moisture measurement, figuring out how to use those in conjunction with a variable rate irrigation map is another one of the challenges that we have. So here's one of those sensors, one of the John Deere sensors, real-time sensors. So it takes measurements down to about 4 feet. I don't think this has changed, but throughout the course of the project, the last 3 years anyway, these were just for lease. So they would lease them to the farmers. John Deere themselves would come out and install them, do all the maintenance, run the websites, everything. And at the end of the year, they'd come get them again. And they were quite expensive. So if you needed, to the point where it was really only practical to install one of these per field. Well, if you've got a very uniform flat field, that might work. But in most cases, we don't have that, right? So figuring out how to best use this over the course of on a field scale is challenging. But these are really great sensors. Like I said, you just log on, and here's the kind of information it gives you. It tells you just your basic soil water content. And then they also give you these lines here, one indicating that you're at a full level in your profile, and one where you're allowable depletion. So essentially, you can get online every day, check this, and as soon as you see your soil moisture content fall below this allowable depletion line, you can turn on your pivot. And that's great as long as these lines are correct, right? So as long as everything's calibrated correctly, it works great. Get into a situation where we were running across several different soil types just all the way down on this thing. It kind of can complicate your measurements a little bit. So, but these do work very well. We've been very impressed with how they work. And they're really neat pieces of technology. It's really, even, the things I've said where we might need a bunch of them, it's still really beneficial for the farmer to even have one of these out in the field, especially on a representative soil type for his field, to be able to look and see real time what his soil moisture status is. That's a really good tool for the farmers to be able to access. Okay, so the next thing I mentioned is we're trying to bring into consideration some of the some sensor issues. How can we use sensors that measure crop status, both nitrogen-wise and even water-wise? How can they help us? With kind of the end goal being, well, maybe some of these sensors are mounted out on the pivot as it goes around the field, gives us some information, talks to the sensors in the soil so they can kind of compare notes, and then is all related to the variable rate system and uses the best information available both from the canopy status and from the soil status to then variably apply the water we have. So one of the things we've been using are crop canopy sensors. These sensors, how I've used them in the past with determining nitrogen status of the crop, they do a really good job, and basically they emit both a visible and a near infrared wavelength down to the crop canopy, and then that light, the visible and that near infrared light, can either be reflected, transmitted, or absorbed by the plant, right? We measure the amount of light that is reflected, and different plant characteristics are going to affect how much of that light is reflected. And we're interested in the nitrogen status of the plant. So essentially, we're interested in nitrogen in the chlorophyll content of the plant. And a really healthy plant, in terms of its nitrogen status, will give you a different reading on the sensor than a plant that is stressed. And then you can use that as comparisons to and algorithms that have been developed to apply nitrogen based on what the sensor tells us. And they work very well for nitrogen, but we thought there isn't any reason why these sensors can't also tell us some things about the water stress of the plant, right? So if this sensor can tell us what's going on in terms of our nitrogen health of the plant, tell us what's going on in terms of our water health of the plant, that would be really beneficial information for this interaction of VRI and variable rate nitrogen. So here's kind of the rig that we got cobbled up here that we used for the first year. This is a mountain bike that has been modified in the seat post here to hold several sensors. And then on the handlebars, there's a place to mount the computer. Can you tell that a grad student was entrusted with doing this work? Because at Brule, he had to walk across that field 16 times back and forth to gather this data. So a lot of work involved. And you can see we've got 2 different crop canopy sensors mounted here. We have an ultrasonic height sensor. It just sends out a sound wave and then records the amount of time it takes for that sound wave to reflect back. We can then determine how tall the plant is, which is a really good indication of our plant health. And then there's a thermal sensor as well that basically tells us how hot the plant is getting. So after the first year of his project, he came to us and said, this is not a good idea. I don't want to push that bike through the field anymore. So we were able to actually find an old detasseler tractor that things were mounted to. And this is what it's looked like for the last couple of years. All the sensors again mounted and can drive through the field. And you can see here, we're in one of our low nitrogen, low water portions of the field right here. And you can see there's quite a bit of visual difference as we kind of move through the field. But this made it a lot more effective to gather the data. Instead of a 2-day project, it turned it into about a half-day project, which really helped everything out. And also, from a safety standpoint, you know, you're pushing that bicycle through 8-foot tall corn when it's 100 degrees outside. It just wasn't a good idea. So this was much better. And we're able to gather a lot more data this way too. We're able to go far more times. Okay, so this just kind of shows some of the work we've looked at on how well the sensors work for determining the actual nitrogen content of the plant. So if we take measurements of the plant, get the readings from the sensor, tear that plant apart, analyze it for its nitrogen content. That's what we've done here in both the leaves of the plant and then the remainder of the plant after the leaves have been removed. And you can see there's a very high correlation, very high R-squares. And this just shows that the sensors are very good at determining the level of nitrogen that is contained within that plant. R-squares of about 0.95, or yeah, 0.95 and about 0.94. So highly correlated with how much nitrogen there is in the plant. So we know the sensors do a good job there. Then we use the sensors to see if we could look and see if there's any kind of water. These are the same sensors, originally designed for the nitrogen stress aspect. We want to see how they did on water stress as well. So what we did is we looked at 100% field capacity plots, 75% field capacity plots, 50% field capacity plots, and then no irrigation. And then we moved the sensor into different configurations because putting that sensor over the corn tassel can actually affect the readings. So we wanted to look and see if we could negate that. So this inner row just means that we move the sensor between the tassels above the rows. 45 degree means we move the sensor down into the canopy and put it at a 45-degree angle. 90 degree means we just move the sensor into the canopy, put it at a 90-degree angle. And you can see all of them did a really good job across the different water stress levels. And this was taken at the R5 growth stage. So this is encouraging. This suggests that the sensors are not only good at determining nitrogen stress, they're also good at determining water stress as well. So then the question came up, well, what if we've got both occurring at the same time in the plant? And that's what we've got a PhD student working pretty much solely on that particular question. If we use this sensor on a nitrogen stressed and a water stressed plant, are there ways that we can determine the differences between those two things, looking at different indices or different ways that the sensors or different sensors that can be used? So he's unfortunately, I don't have any good results to show you on that yet. He is finding that there are different indices that work better for the nitrogen side of things and the water side of things. Next thing I wanted to do was to see if there was any correlation whatsoever between what these sensors were telling us and the actual soil water content. And when we first started out, we were seeing a really good correlation. Right? We were seeing soil water content levels increased as our reflectance increased as well. So that was encouraging when we first started. Then this was taken at the R3 growth stage. And the water was collected over a depth of 1 to 3 feet. Then we had a rainfall and went out and took the same measurements again. And what we can see is when that rainfall occurred, the soil moisture readings changed quite a bit, but our sensor readings didn't change that much, right? So relating what the sensors are telling us in terms of soil moisture content really doesn't appear to be that. In certain cases, it looks like it'll do a good job for you, maybe if it hasn't rained for a really long time. But as soon as we get that rainfall, or if we got that irrigation event, it kind of changed things quite a bit, and it really wasn't a good correlation anymore. So that just kind of tells us we really need something measuring our soil moisture content and something separate that's measuring our plant canopy measurements as well. And then find a way to kind of integrate both of those measurements. Okay, so back to the rural water lab. Here are the yields we got based on our fertilizer rate in 2012. And as you can see, we have no end response whatsoever. Here are all the irrigations that we had, 40%, 70%, and 100%. Now, we can see that as irrigation increased, our yields increased. As our nitrogen fertilizer increased, we saw no response whatsoever to nitrogen. This happened in 2011 as well. We cannot explain it, but we think it has something to do with the level of variability we have in this field. Somehow we're not accurately or completely quantifying that level of variability that we have in this field. It's, like I said, it's very complicated. Now, at our South Central Ag Lab site, we did see a really good interaction between the nitrogen and the water. It's a far less complicated site. We saw, as you might expect, as water increases, yield increases, and then nitrogen uptake increases as well. But at our rural field site, due to the variability, we're having a tough time trying to quantify what's going on out there in terms of varying our water and our nitrogen. Then here's the results from last year. And for the first time in 3 years, we got a nice nitrogen response. So as we increased our nitrogen, we increased our yields. On here we see the irrigation levels, and we see no differences across our irrigation levels. So we looked into that, and what we discovered is the variable rate irrigation system at some point early in the season stopped functioning. We think, like I said, we think it was struck by lightning. And the good thing about the system is that if it defaults, it goes back to 100% irrigation. So you're not losing your irrigation water. So essentially what you're looking at here are 3 100% irrigation treatments. So this speaks to the issues we've had, the growing pains with this emerging technology. We don't know exactly when it failed, and when we did realize it had failed, we were unable to fix it. We just didn't have the capabilities to get it fixed in the middle of the season like that. So these are some of the growing pains and some of the issues we've had. And like I said, one of the things we're hoping to really fix as we move into this brand new system. So, like I said, when I first got this system, I was really excited. I thought it'd be something turnkey. You throw it on there, you type in your rates, and you let it variably apply water. We're finding it's not that way at all. It's a system that requires a fair amount of maintenance, a fair amount of babysitting, and a fair amount of upkeep to make sure that everything's working properly. So that brings us to some of the considerations that we've learned using these variable rate irrigation systems so far. So first of all, the economics involved, right? Do you have a field to where you can accurately quantify the differences you have out there, and you will see a benefit from varying the amount of water you put on? Maybe in a really high productive area, you can put more water on. In a lower productive area, you don't put as much water on. And do the economics pan out? Now, for guys that are under allocation, that might be a very simple yes. For guys that have relatively uniform fields, the answer is probably no. And then in a field like ours out at the Rural Water Lab, where the variability is so high that we're chasing our tail the whole time, the answer might be no as well. So that's just one of the things we need to look at. Second is the accuracy and the performance of the systems. I kind of talked about that a little bit. Obviously, this is emerging technology. It's going to get better. But we're trying to say we want to change water exactly at this location because this is where we've quantified this new soil type happens. Well, if that system doesn't change over right there, if you have a 20-foot delay, or if you got to go out there and spend a couple days moving that pivot back and forth, getting it to turn on exactly where you want, it might be more trouble than a lot of guys are willing to put into it to be able to do that. I expect that this is going to get resolved as the technology kind of emerges. Secondly, the recommended application rates. This is going to be site specific. Just like that's one thing we know for sure. So a map's going to have to be developed for each individual field. So figuring out exactly what's needed, where it's needed, is soil texture for this field the right way to go, or do we need to do something else related to some other measurement that we're having? Then the interactions with other inputs. We start going out to the field and say, okay, we're going to put on X amount of water here and Y amount of water here. How does that change not only nitrogen, how does that change our herbicides or our fungicides or anything else? So there's a lot of really good agronomic questions involved with once we start to vary this water. And then again, what other sensors are we going to need to really make this technology function to the level that we want it to function? And I've kind of talked about a few of them, but there's a lot of other research being done trying to figure out not only which sensors might help us best do this, but how many sensors we have and what kind of network of sensors do we need? How many do we need in the field? All those kinds of things. So there's still a lot of information that we're trying to figure out, a lot of research to be done, a lot of job security, I like to say, in dealing with a lot of these things. But we have seen, and I have talked to a producer near us that he's under allocation, and this last year they came to him later in the season and said, you've only got X amount of water left. And he had a system out there, and he was able to take it and start to apply that water to the area of the field that he knew was going to yield the best. That way he was able to do the best he could with the water he had left. So we do think there's a really good potential to increase water use efficiency using these systems, and that there's still quite a bit of work to do with them. So with that, that's all I have. That's all I have for you guys. So I'd be happy to take any questions if I can answer them.
Very good. Thank you, Tim. We have about 10 minutes for questions for Dr. Shaver, and for the purpose of the video, if you have a question, I'd like to bring the microphone to you. So do we have any questions?
Tim, when you were talking about using the crop canopy sensors as an indication or showed that they were related to water status, how are you going to separate the longer term effect of biomass production from the more instantaneous indication of water stress that you might want to use to decide when it's time to irrigate?
That's a really good question, and I would really welcome your input on that because I haven't quite figured that out yet. Yeah, so the biomass change, that's a big part of it, and that's something we're trying to figure out and we're struggling with. So I don't have a good answer for you on that.
I had a question.
Get your exercise, Derek.
Is there any potential for remote sensing to help out with this, or is that just the resolution with that not really applicable here?
I think there's a huge potential for remote sensing to help with this, and there's Richard Ferguson, who's a big part of this project, is really involved with UAVs. So that's one of the things that we're looking at is flying specific sensors out over the field with these UAVs to try to help us figure things out. You know, one of the issues with this irrigation thing is it's usually pretty immediate. We need to get an answer. We need to start. You don't want to water stress for very long because you start to hurt the crop. So it needs to be something that's immediate, and that's where we think these UAVs might be able to help us more than what you'd consider a traditional remote sensing platform like a satellite image or have a flight come over. So that is something we're considering, and I think there's a big potential for that to help out here. I don't think there's going to be any one thing that you really say, okay, we're using this to help us figure out the best way to do this. I think you're going to have a network of sensors and other information devices that all talk together in one way or another that are all communicating with the pivot real time, where all of this can be kind of fine-tuned as it's moving through the field. I think that's a long ways off, but that's kind of the vision I have for it.
For the John Deere sensors, did they tell you volumetric water content or soil water potential?
It's volumetric.
You showed that one of the methods of determining the soil variation is the EC mapping. Mm-hmm. And you also mentioned that, when you have, let's say, a shallow soil or sandy soil, then you may apply less water. However, when you do that, that means you apply more water to the more productive side of the soil. If you apply this principle of diminishing return, when you apply more to the better spots, you also will, basically your efficiency will be lower or start to decrease. Mm-hmm. So how do you balance this kind of contradictory between applying more to the better spots and then less to the.
Right, and that's one particular theory that we're looking at, or one particular, but we're also looking at the other ways as well. So we're trying to look at all the potential. So we're also looking at, in that bad area, we're applying the highest amount of water, and in the best area, we're applying the lowest amount of water. So we're looking at all the different variables involved to try to help us figure out what is the best and most efficient way to do this. So it's just, that was the example I talked about, but that's not the only thing we're looking at. We're trying to figure out all the different variables involved with that, but that's a very good point.
Two questions. On your slide that talked about grain yield, and you indicated that when you added more water, you had better production, but when you added more nitrogen, you couldn't see the relationship. Was the amount of nitrogen in the irrigation water taken into account?
Yeah, our water was tested and it's very clean. I think we're at about 2 ppm nitrates.
Okay.
Yeah, so we have very clean. That was the first thing we looked at.
The second question that I had is there any work being done in terms of the amount of nitrogen getting past the root zone in the study?
No, and that we would like to bring that the leaching part of it, we would like to bring that in, but that at this time we have not done that yet. But that is something we'd like to add. And then the question, talking with some of the people earlier today, is the next logical step is fertigation. What happens with these variable rate systems, we can variably apply water through the pivot as well. So those are the kind of the two areas we'd like to bring in next, is the fertigation and the leaching part of it.
With the assumption of variable rate irrigation, I guess it would suggest that you're varying it from some known amount. Have you calibrated the existing equipment to understand how uniformly, or do you have some understanding of what the range of variability might be in the initial system before you start implementing variable rate?
Yeah, so we did calibrate it, and our system was actually fairly uniform all the way across, and that's when it was all running at 100%. When you start to change the rates, things do change a little bit. So yeah, there probably is a fairly large calibration that needs to be done when these systems are first used, so you do know exactly what you're applying, because what does 50% mean, of what exactly? So yeah, that does need to be done. That's not something that's being done in a lot of the systems. People just assume that, well, I know that my 100% rate is 0.6, so I must be putting 0.3 down. And that's a big assumption that's being made that may or may not be true. So that's a very good point. Calibration is something that needs to be done if you're really going to fine-tune these systems and what you're applying. These systems were first kind of created kind of down in the southeast, where they have a lot of ponds in their fields. And the guy said, well, why am I irrigating my pond? Why can't I just turn it off over the pond? And so it was just a very simple on or off setup when they first came out. And now, out here where we irrigate in the West, we want to use them for far more than they were originally designed for, and I think that's why we've had some of the growing pains that we've had. But because of the interest in them, because of the people can see how important they could be for helping us, they're getting better and better all the time. At least that's my 2 cents on it. So.
Time for one more question, if there is one.
Okay, well, thank you very much.